Okay, in last lecture we have seen IIR filters in comparison to FIR filters, and we have also gone through the condition why we cannot have a linear phase response in IIR filters, and we have seen the practical limitation of making an IIR filter realizable. So we have seen those particular part in last lecture. So today we will start our discussion with designing of IIR filters. So this is our topic, designing of IIR filters. Now the process goes through the multiple steps. The process of designing IIR filter goes through the multiple steps, and those are: first, design of IIR filters from analog filter. So this is our first point, that we want to design an IIR filter from the analog filter. In this case, the first step follows is transform the given digital filter specifications analog filter specifications. Second part is design an appropriate filter in terms of HS. Now third point is transform the analog HS to a digital filter FJ. Fourth point is apply frequency, band transformations to obtain frequency selective filters, maybe high pass, band pass, and band stop. This conversion is generally for low pass filters. Now this approach is called approach 1. We can have an alternative approach, and we can have another 3 and 4, which is apply frequency band transformation, in S domain and obtain another frequency selective filters, which may be high pass, band pass and band stop. Then at fourth step we will convert or we will transform analog filter HS to digital filter HN. And this approach is approach 2. We can apply any of these two approach to obtain an IIR digital filter. Okay. In both approaches, there is one point which deals with transformation of HS to HZ. That's mean mapping of S to Z. Now this is very important point, and throughout our discussion of IIR filters we will focus at this particular point, that is mapping of S to Z. Now there should be condition for transformation from S to Z. We have to keep in mind these conditions before applying transformation between S to Z. First part is S is equal to sigma plus j omega, and j omega axis of S plane should map onto the unit circle of the Z plane, and we want to clear certain points. That means omega is analog frequency, omega is digital frequency. We know the limits minus infinity omega to infinity, whereas this omega will vary from minus pi to pi, that we have already seen. So j omega axis defines the Fourier transform existence. In analog domain. In a similar manner, unit circle at mod z equals to 1 defines the Fourier transform existence in digital domain. So these two are important point, that this j omega axis should map over the unit circle of the Z plane. This is the first condition. Second condition is the left half plane of the S plane, sometimes also called LHP, should be mapped inside the unit circle. Now this condition is important for the stability of the filter. For an analog filter to be stable, its poles should lie in LHP, and for IIR digital filter to be stable, its pole should lie inside the unit circle. The digital part we have already discussed in our previous lectures. This analog part we will discuss in support lecture. After the conditions for the transformation between S and Z, now we can represent analog filter into multiple forms, such as first, HAS can be written as YS over XS, where we have provided an input XS and we have obtained an output YS, and this is the transfer function, analog transfer function of an analog filter, can be written as summation k equals to 0 to m beta k s to the power k, and then summation k equals to 0 to n alpha k sk, where alpha k denotes for the poles and beta k denotes for the zeros. So this is one of the case in which we can represent the transfer function of analog filter, and in second part we can directly write HAS equals to minus infinity to infinity HAT exponential minus ST dt. And in third case, which we can derive from the part 1, we can multiply alpha k sk with ys and xs with beta k xk, which will give summation k equals to 0 to n ys alpha k sk is equal to summation k equals to 0 to m xs beta k sk. Rearranging, will get summation k equals to 0 to n alpha k sk ys equals to summation k equals to 0 to m beta k sk xs. Now taking the inverse of Laplace transform, we will get the output as summation k equals to 0 and alpha k del k by del t k into yt equals to summation k equals to 0 m beta k del k by del tk into xt. We have used a property of Laplace transform called differentiation property, that is, if xt's Laplace transform is xs, then del xt by del t will give as xs minus x0. In this case, x0 is the initial condition, and we have assumed it to be 0. That's mean the analog filter which we are dealing right now, we are assuming that at initial state it is relaxed, so there is no initial conditions. So with this particular point we'll end this lecture. In next lecture we'll start with the different methods of IIR filter design. Thank you.